All right, today is a Monday of a 3-day week, which is great. Still really cold out, which is not great, but so nucleophilic substitution is short for Sn1 and Sn2. S substitution and N nucleophilic substitution nucleophilic. So substitution, nucleophilic substitution. It involves halogen alkanes. Halogen alkane, so that's alkane, carbon-hydrogen compound with a halogen attached to it, saturated with hydrogen and halogens. CH bond is nonpolar, but the C halogen is polar because of the electronegativity difference, the greater electronegativity value of the halogen. Requiring a different mechanism. Between carbon and halogen, partial charges form due to electronegativity difference, and carbon forms a partial positive and is said to be electron deficient. So if it's electron deficient, that means the electrons are not around it. So therefore the charge, partial charge, would be positive. So something that's electron deficient is going to be more positive, partial positive. Okay. All right. Nucleophilic substitution. There's two pathways, and you guessed it. It has to do with what type of carbon the halogen is attached to. So you got what? Primary, secondary, tertiary. Anybody know the difference between those three terms besides their spelling? 1, 2, and 3. That's pretty much it, yeah. 1, 2, and 3, how many carbons are attached. So primary means that the halogen is attached to a carbon that's only attached to one other carbon. Secondary, the carbon's attached to 2 other carbons. Tertiary, the carbon is attached to 3 other carbons. So, let's see, we got Sn2, Sn1, so it's just kind of generic. Nucleophile, ooh, who wants to read that? Oh, Swanson.
11 rich reactants that have a high electronegativity value.
All right, so nucleophile is electron rich, so it's going to be a partial positive or negative. Partial negative because it's electron rich. SN reaction, substitution nucleophilic. Next is heterolytic fission. Alexandra, do you want to read that one?
No, not really.
Okay, we'll get. Oh, Dobson. All right.
Oh, you're here?
No one brought that
fission. When C halogen bond breaks, an halogen atom is released as a negative ion halide, sometimes referred to as leaving group.
All right, nice job.
Popcorn.
Well, no, that was the end of the section.
Read the equation.
So heterolytic fission, when carbon-halogen bond breaks and the halogen atom is released as a negative ion. So looking at this, we got fission happening right here, heterolytic fission between the carbon and bromine, and it forms a negatively charged ion. If you're starting with that, like right here, this would be considered like a nucleophile. Why? Because it's electron rich, which is why it's negatively charged. So it's a substitution. It's kind of like, what do you call it, Newton's cradle? Those little balls that go back.
Yeah, those are cool.
So OH is 1, it smacks against the carbon and boots out bromine. But we got to look at certain situations, and it depends upon what type of carbon, whether it's a primary, secondary, or tertiary. So we got Sn2. Looking at it. Yeah, Sn2 is going to be the Newton's cradle thing, where you're going to have a temporary conformation right when the ball hits all the other balls, and then the actual product. So we got curly arrows to kind of show the order of happenings. Little curly arrows. So a curly arrow is an arrow that's not straight. It's curly. Represents the motion of an electron pair. So starting point right here, we got OH. What would we call OH in terms of organic reactants? Nucleophile. You got it, because it's electron-rich attacking group. And we got the first curly arrow. I'm going to put a little 1 right there. And this is creating, they don't show it, but you know, technically the temporary conformation would be, actually that should be a dash, sorry, that's a dash. Dash. And this dashed line right there just shows that it's going smack dab at you, and this solid triangle is showing that it's into the page, trying to show 3 dimensions. And this is supposed to be a dash line to the chlorine and a dash line to the OH, showing a temporary conformation, that moment in time where they're both there. But it's the one that's a little bit more stronger of a nucleophile that's going to take hold and stay. In this case, chlorine is not that one. So it's going to leave, and we call that the leaving group. I don't think I have that written down there, but leaving group. And you could call the OH the attacking group. And the OH is essentially substituting the chlorine. And the chlorine is then the electron-rich entity on the outside, booted out. So it starts with the OH, attacking in this temporary conformation, and then the chlorine leaves. So that's Sn2. And what type of carbon is this, would you say? Primary, secondary, or tertiary? Well, if these were hydrogens, it'd be tertiary, but if these were carbons, it'd be tertiary. But they're hydrogens, so really it's just this carbon is attached to technically no other carbons. So we consider it a primary. So Sn2, do I have that written? I don't. Oh no, I do right here. Sn2 is for primary. Haloalkanes. If it's tertiary, now you got to go through the Sn1 pathway, because you've got something called steric hindrance, and steric hindrance is side chains getting in the way, messing things up. So basically there's no availability for a nucleophile to attack this carbon. It can't get in. It's booted out. It's prevented by the alkyl chains. So what has to happen is it kind of has to be strong enough to be able to like use the force to be able to compel the leaving group to actually leave. So the leaving group leaves first in Sn1 if it's in the presence of a strong enough nucleophile. So what starts the reaction? The presence of the nucleophile does. Will every nucleophile cause the reaction to go? No. All right, so what we got right here, first step, leaving group leaves, and you form a carbocation intermediate. That's what this is called. Carbocation intermediate, where chlorine is electron rich and it's off by itself, and then we got this carbocation that now has a bonding site that's available. Perfect timing, because this OH nucleophile wants to go in and substitute the chlorine. And it can now, because there's an active available site. And then it produces the same molecule just without the chlorine but with the OH. So the key to this is there's a carbocation intermediate stage where the leaving group has left, forming a positively charged carbon entity. Pretty much it. So we got a bunch of little terms here. We got Sn1 stands for substitution nucleophilic, unimolecular, meaning that it's simply just one molecule and then the leaving group is leaving, whereas bimolecular for Sn2 requires basically the two reactants interacting. Works only for tertiary halogen alkanes. I would underline that. Because we know Sn2 only works for what? Primary. Sn1 only works for tertiary. Got this term called steric hindrance. Bulky alkyl groups make it difficult for an incoming group to attack carbocation, hence this Sn1 pathway. Carbocation, carbon atom with a temporary positive charge. Carbocation is stabilized by 3 alkyl groups, allowing for it to last long enough for a reaction to occur. Positive inductive effects like donating electrons that produces temporary stability. So is it stable? Not really, but it's stable enough to allow this pathway to work. We might have a question about secondary alkenes. Which pathway do they do? Well, they get to choose. They can either go Sn1 or Sn2, and it does depend upon, you know, the overall molecule. But that's going to be beyond this course, so you're not going to be asked the question about a secondary haloalkane, because it could go either way. Hey, we got some practice. All right, here's some practice. Hey, yeah, that was going to be my question. This is tertiary, so which pathway, Sn1 or Sn2? Sn1. For G, is that primary, secondary, tertiary? Primary, so the pathway would be Sn2. And the last one would be, that one's secondary. If we were taking an IB test, would they ask a question like that? No, they wouldn't. They wouldn't. All right, so try E, G, and I guess that one doesn't have a letter. I think it should be A, but it's E. Yeah. Yeah. So, guys, this is tertiary, so we got to do Sn1, which means it's unimolecular and something's formed. Carbocation Intermediate. You got it. So we got to draw that. IB's going to want that. And the positive charge is going to be where the halogen once was. Oh, we got to do curly arrows too. So the first thing that happens is in the presence of a nucleophile, the Br skedaddle. So we got to show the electron pair that's formerly in the bond between the Br and the C is now heading back to the bromine to make it a Br negative. So here's the carbocation intermediate. And then what we have going on here, what is this? This is an ethane of some sort. 2 oxygens and a hydrogen. Is that a carboxylic acid? Usually I see it as COOH, but yeah, they're kind of being fancy by saying CO2H. So this is a carboxylic acid. And typically with acids, what do we know about the H+? What happens to it? It gets tossed away. So technically this would be like an H+, and something like that. Like organic acid-base chemistry here. All right. So this is ethanoic acid right here, and the H+, and these are how they are in solution, in their ionic solution. So we got negative. Hey, that looks nucleophilic right there. Electron rich. Probably going to attack. So we got to show that in the curly arrow, attacking the carbocation electron deficient region. So then we're basically going to show what the final product is. 2 curly arrows, leaving group leaving, the nucleophile attacking. I guess you could number it 1 and 2 if you wanted to. And then we would write, ooh, does this look like what type of functional group is that? It's an ester, you got it. So, we just made an ester. So that's kind of a different way of making ester than what we've talked about. But yeah, so are there different ways of making the same functional groups? Yes. All right, anybody remember what pathway that was? Sn1, because it was a tertiary haloalkane. All right. So here we got a primary haloalkane, so it's got to be Sn2, which is the Newton's cradle version. And you do have a very, very temporary intermediate conformation. What happens first? No, this one's just got to be like a battering ram, and it's Newton's cradle. So we got the action of the nucleophile. So Sn1 is unimolecular, meaning just the presence of one reactant, essentially. It's a one one-ship deal, whereas SN2 is bimolecular, meaning there are two reactants interacting for it to happen. So OCH3, this is the nucleophile, and it's going to attack the electron deficient carbon. Which one's the most electron deficient? It's this one next to this very electronegative chlorine. It's kind of hogging it in this sharing covalent compound deal. So we got like a partial positive here. That's a weak spot, so OCH3 is going to take advantage and attach right there. And we got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Here's this. Okay, and then what we're going to do is we're going to have Cl is kind of now not as attached, and OCH also is not too attached. This is just a very temporary conformation. And what's going to happen then? In Newton's cradle, once you have that one moment where they're all together, the balls, they split again. And the chlorine is the leaving group. And that is that.
Why does the arrow on the CL just point from like the line to CL?
This is just talking about the electrons that are involved in the Cl-C bond are going back to the chlorine. So it's going to. So technically, we got plus Cl minus. So the two electrons are involved there. It would probably make salt because you still got sodium Na plus from there. All right. The third one, this is SN. No, it's a secondary. So it could be either SN2 or SN1. Just for practice, what do you guys want to do?
SN2. Wait, 1.
SN1.
No, wait, yeah. 1.
Okay. SN1. So this is a cyclohexane with a methyl group and an iodine coming off. And let's just say this is an SN1 pathway. So what happens first? Very first thing.
Iodine will go away.
The iodine goes away. You got it. The iodine is the leaving group. And what forms after it leaves? Carbocation Intermediate. So we got to show a little plus charge there. All right. And then it looks like we've got SCH2CH3, so Na plus. S is probably the negative portion. And this S is going to attack the carbocation, the electron deficient region. CH3. Then we got that. Oh, that looks like it. That's it. And then we got sodium iodide probably is produced. So really, the beginning and the end are going to be similar, whether it's SN2 or SN1. The big difference is going to be the intermediate. Here we got a temporary conformation where they're both attached. Here, you never have a situation where both reactants and products are attached at once. Here's some facts about SN1, SN2 reaction. So in terms of quicker reaction rates, tertiary or SN1 pathway is going to be quicker, then the secondary, and then the primary. So the primary is going to be a little bit slower. You won't be asked too many questions on that. Decreasing electronegativity down a column means the carbon of the carbon-halogen bond becomes progressively less carbon deficient. So fluoroalkane should be the most reactive in that case. Increasing electronegativity.
I want to make one. Our class is the best
There we go.
class ever.
Did any other Pride periods participate? We had a photo of 6 people in there.
Alex, you want to be wearing to the Yes. Yeah, wait, where'd the scissors go?
Sorry. You gave them to Natalie. That's why I got hit. Oh, never mind. You gave them to Natalie.
Okay, so what this paragraph right here is saying is there's different ways of looking at it. If you're looking at electronegativity, it's going to say that fluoroalkanes are the most reactive. If you're looking at bond strength, then iodine is going to be the most reactive. And experimentally what shows is iodine is actually going to be more reactive in this situation. So if you have, like here, iodine versus chlorine being the halogen attached, this reaction is going to go quicker with the iodine through experimental results. So you might want to highlight that. If you got to remember something, think, okay, iodine is going to be the most reactive. You probably won't be asked anything about that though. Okay. Speaking of cations, I think that's why this illustrator decided to use a cat as an analogy.
Were you the illustrator?
No, I was just I did use Google to find that image, but I was the Google browser person. I thought, yeah, that's a pretty good picture because we got Sn2 versus Sn1. Which picture, let's say this is one, and then the bottom row is another story. Which one tells the story of Sn1? The top one, you got it. So this cat over here uses his mind power to compel this cat to leave.
I knew it, Jenna.
And he goes in. Whereas Sn2, there has to be an interaction between the two cats. So bimolecular. And that cat is being forced out. All right. All right, so we're not going to get into that too much. IB mainly wants you to know Sn2, Sn1. Those are the biggies.